Okay.
I think we can go, right?
So, hello everyone. Pengcheng Xu is a second year.
Haosong, sorry again. Just wait a second.
Okay.
Yeah, awesome.
Okay, we can start.
Okay. Hello everyone. Pengcheng Xu is a second year master's student in computer science. His research interests are mainly about computer systems, including operating systems, embedded development, and FPGA development. Today, he is going to present the paper Multiscalar Processors. Yeah, Pengcheng, please.
Okay, thank you very much, Haosong. Hello, everyone. Welcome to my presentation of the paper Multiscalar Processors by Professor Guinda S. Sohi and other co-authors at the University of Wisconsin-Madison. So this paper was first presented on the International Symposium of Computer Architecture, also well known as ISCA, in 1995. So before we get started with the presentation of the whole paper, let's take a look at the executive summary. So the problem the paper presents is to improve the performance of sequential execution. This has been the glory arena of how processors improve their performance when to execute sequential programs. And the goal the authors try to achieve with this paper is to execute as many instructions as possible per cycle. This metric is also well known as instructions per cycle, or IPC. The key idea the authors employ to achieve this goal is to improve the instruction level parallelism, or ILP, through what the authors call the multiscalar paradigm, which divides the program into a collection of tasks to increase instruction level parallelism. The mechanism they use to achieve this idea is after dividing the program into a lot of tasks, each task is then assigned in runtime to one of the many processing elements. We will denote this as PE, as runtime for independent execution. The results the authors present in this paper is multiscalar processors significantly improves instruction level parallelism in parallelizable workloads. So let's take a look at the agenda of the presentation. So first, I will introduce a few basic concepts that is of importance to this paper. And then we have a detailed walkthrough of the multiscalar paradigm. And then we have, after that, we have design analysis of the multiscalar paradigm and hardware design. And following that, we have the evaluation of a sample design proposed by the authors. And I will present the strengths and weaknesses of this paper. And finally, I will open the discussion for the audience. So let's get started. So the basic concepts of this paper is all about instruction level parallelism. Let's introduce and walk through. Let me introduce a few classical paradigms in instruction level parallelism. So first of all, we have to talk about pipelining, which means execution of multiple instructions can partially overlap in such a design. Let's take a look on the right side where we have from top to bottom, we have the passage of instructions in the pipeline design, and left to right is the passage of time. So we can see that in a specific time, the 5 units inside the whole pipeline, that is instruction fetch, decode, execution, memory, and write back are active at the same time, denoted in these green boxes. And what is important to note here is that in the pipeline, in the pipeline design, the throughput of instructions is still 1 instruction per cycle. Does anyone in the audience know why do you have pipelining in this case? Please.
Because maybe the results don't depend on each other. So here
Yeah, that is possible. Yes. Do you have another idea? Yes, that's a main reason we have pipelining of instructions, because as the whole pipeline gets more and more complicated, it takes way too much delay for an instruction to execute. So we break them into smaller pipeline stages to maintain the same throughput while being able to increase the frequency. Okay. The next relevant concept, or say paradigm inside instruction level parallelism, is superscalar. So this is not a single design, but rather a concept that says we are able to fetch and dispatch multiple instructions at once. This can actually be of any implementation so long as the throughput of the instruction stream is actually greater than 1 instruction per cycle. Let's take a look on the right side where we have what we call a 5-stage dual issue in order pipeline. So the 5-stage and in order characteristics is the same as the last slide, but we have dual issue. So every cycle in every specific time we issue 2 instructions. So we can see that we have double amount of the pipeline stages. We also have double amount of throughput. Yeah. What's important in this in the superscalar paradigm is that we use a single program counter to step through the entire program and establish a window of operations that are executing simultaneously. Yeah. And after seeing this dual issue in order pipeline, let's take a look at another way of implementing superscalar, which would be out of order. It's by far the most popular way of implementing out of order. That was the case when this paper was published. That is still the case today. And I mean, in terms of traditional CPUs, let's not talk about like GPUs or whatever at the moment. And out of order actually means instructions they can execute in any order that does not violate data dependencies. Here, the data dependencies are defined in a way that we call memory models or consistency models. So if anyone knows about x86 memory models, there's what we call total store order. That is one possible memory model. And this paradigm is usually coupled with multi-issue. So for example, if you have a 4-issue or 6-issue out of order machine, that will then give us superscalar throughput. On the right side, we can take a look at this like block diagram of a very classic out of order machine. That is the Intel x86 Pentium. I think that's the i686, but correct me if I'm wrong. Yep. We have 6 ports. You see in this like purplish section down there, we have 6 ports which issue different groups of operations that's carried out by the machine. The next paradigm that's important for this for the context of this paper is data flow execution model. This is a quite special paradigm, especially in comparison to regular scalar or superscalar paradigms, because instructions execute in this paradigm. Instructions execute once input is available. That means we don't really have what we call a program counter traditionally. This is like the data arrive at the ports and then they get the computation gets carried out. Let's take a look on the right side in the red box. We have, so basically this is the simplified vector dot product. I mean, the actual data flow, that diagram will be a bit more complicated because of control flow information. But here we have, basically we load A and B from the A and B vectors as scalars, and then we multiply them together. We then add them to the partial sum inside the buffer. Yes, this paradigm is mostly used in digital signal processing and high-level synthesis because it's quite difficult to build general-purpose processors out of this paradigm. The reasons we will talk about later in the discussion. So we have a very important observation of the previous mechanisms introduced. That is, most instructions executed are actually independent on each other. That means a sequential execution plan does not really exploit such independence in terms of improving parallelism. The key constraint in previous methods that also is that we stall instructions until they have all their control and data dependencies resolved. That is also the case for out-of-order machines. If you think of, like, we have a lot of what we call hazards in out-of-order machines. For example, if you have load after store or store after load, that will result in the instruction stalling. That is what the stall instructions I'm talking about here. Okay, so that concludes the introduction of basic concepts. Let's move on to the multiscalar paradigm, which is the most important section in this presentation. Let's take a look at the agenda. So first, I will introduce the basic philosophy and a few important concepts for the multiscalar paradigm. And then we'll take a look at the multiscalar programs, and finally, a proposed example of the multiscalar hardware. So the most important key idea in the multiscalar paradigm is we need cooperation between hardware and software. The way we do that is we have the compiler statically split the program into tasks using what we call the control flow graph. I will introduce what a control flow graph shortly, but in case there are any compiler guys down here, they already know you will already know what a control flow graph is. And after having the split of the control flow graph, we then in runtime speculatively distribute these tasks into parallel processing elements. The way this works is we have separate program counters inside each of the processing elements, thus each of the tasks to sequence through the entire program. That may sound a bit weird because as programmers, we know that we have a sequential view of the program. For example, if you write C code, we always assume that the program executes from line to line, right? Abstraction still has to be maintained by this multiscalar paradigm. So we then need to resemble sequential appearance by constraining task dispatch and task commit. Yes. So the important concepts would be, the first one is control flow graph. So a control flow graph is a directed graph that controls the flow of a program. Which consists of what we call basic blocks and control flow. So basic blocks are the nodes inside the graph, and the control flow are the edges. Let's take a look at the sample control flow graph. It's like here we have 5 basic blocks, and then, for example, there's one path that we could execute from A all the way to E, but then we see that there's a loop between A and D. That's what we call a back edge. That's like the basic block D can possibly contain the end of a loop. For example, it can loop back or it can continue. Yeah. And inside the basic block, the first instruction is the unique entry of each basic block. And the last instruction is the only control flow instruction inside the whole block. For example, if it's a jump, if it's a call, or if it's a conditional branch, whatever. Yeah. The next important concept is tasks. So we talked a lot about tasks already. What is a task? A task is a portion of the entire control flow graph. That means it is a contiguous region of a dynamic instruction sequence. The dynamic instruction sequence, like dynamic, is important here because in contrary to what we may call a static instruction sequence, which is like if you look at the binary of the program, you see an instruction sequence. That is the static instruction sequence. Dynamic instruction sequence is what happens when the program actually gets executed. So if you loop a lot of times inside a loop, the sequence will contain the entire, like all the iterations of the loop instead of just the loop one time of the loop. Let's take a look at an example of a task. So we have a program that consists of 3 simple tasks. Inside task A, there's like 2 basic blocks. Remember basic blocks from control flow graphs. And then inside task B, we have 3 basic blocks. Yeah. Each task is assigned to a after creation is then assigned to a processing element for execution. Note that tasks are possibly dependent on each other because, as we said, we have control flow dependencies. Like one task should execute after another, or we have data dependencies. So one task may consume the values produced by another task. Yeah, that is important to remember because we're going to use that concept later. And then we talked about how we should impose sequential appearance, how this is important, right? The way we do this, but also the challenge why we need to talk about this in the first place is there's a challenge when instruction per cycle grows greater than 1 is we have to ensure that the PEs adhere to the sequential execution semantics about remember why we need the C program and everything. Yeah, and there are 2 important definitions we need to make clear before we can say we actually maintain a sequential semantics. That is, so first of all, you need to maintain the order between processing elements execution. The second concept is we need to define how we actually do speculative task execution. Let's get into it. The order between processing elements. On the right side, you can see a brief view of how example multiscalar processor will look like. So, but let's take a look on the left first. So we have to ensure the task level sequential order. This is guaranteed by maintaining what we call circular queue of processing elements. We see the circular queue is maintained by see these arrows in here. That's the logic order between processing elements. It will also be implemented by a physical actual ring, but let's leave that when we talk about the hardware. And we have the ring that ensures the order, but it's a queue, so we need head and tail pointers. Between the head and tail pointers, which are marked with arrows on top, it's a bit hard to see, but the tasks between the head and tail pointers are the tasks that are currently scheduled to processing elements. Outside, there's like nothing meaningful. Yeah, and tasks produce and consume values bound to registers and memory. We then need to maintain, we also need to maintain this one single set of registers and memory to keep this sequential appearance, because recall that in scalar processors, we have one set of registers, we have a single region of memory, right? That's why we need to do that as well. So, okay. The next important definition to make is about speculative task execution. So first of all, why do we have speculative tasks? The reason we have those is so we can have control prediction or the control speculation. So that's traditionally known as branch prediction. So whenever we have a branch, we need to decide if we proceed like if it's a conditional branch, if we take the conditional branch or if we don't take the conditional branch. That's control speculation, but there's also data speculation. That means because we just dispatch tasks to the processing elements, ignoring their memory dependencies, we have data speculation. That means there can be possible load and store actions that doesn't really adhere to the memory model. And we resolve the data dependency violations with address resolution buffers. That is one concept that reorders all the captures all the in-flight memory accesses and then resolve them later. But we'll talk about this in more detail in the hardware section. In case of an unresolvable conflict where the address resolution buffer couldn't do anything, for example, or if we made a wrong prediction about the control flow, we then need to squash the successor, which means we have to restore the architectural state to a previous point where we knew everything was settled and before we did this wrong prediction. Yes. And the final requirement in speculative execution is the tasks are retired in the order as they're added, because it's quite obvious that if we don't do this, as tasks depend on value from the previous task, there can be that we retire the second task and the first task hasn't been fixed yet. We can then have committed like wrong value in the second task. So we just say that we ensure the tasks are retired in the order they're added to the queue. Yes. And that concludes the basic philosophy and concepts of multiscalar paradigms. Let's then now move on to multiscalar programs. So how does a program actually look like in the multiscalar processor? So on the right side, we have a very, I would say, quite basic example of searching for symbols inside a linked list. So we can take a look at the source level. We have a loop that loops through a buff-sized number of symbols. And then inside the outer loop for each iteration, we take one symbol out. We then traverse the entire linked list to look for this symbol. And then if we find the symbol, we call the function process on this list element, and then we break out of the inner loop. And if we eventually didn't find that element inside the loop, we then call add list symbol. That means we add this symbol to the list. So that's quite a straightforward example. Let's take a look at how this program will be mapped to the multiscalar program paradigm. So one requirement of the multiscalar paradigm is that a program in such a paradigm should enable fast walk through the control flow graph to distribute tasks onto many processing elements. So recall that we need to speculatively distribute all the tasks. So if we have to inspect every instruction, it's super slow. We just need a way to be able to skim through all the tasks. And that is what happens here. We have the task granularity on the right side marked in the red box. So basically, we choose the task granularity of the one iteration of the inside loop. Recall that we said the task can be greater than a single basic block. Yes, this is a greater than a single basic block because inside we also have a loop and also a lot of branches. So apparently it is greater than that. And then an important hardware component called the sequencer. We will talk about that a bit later, but the sequencer is this thing inside the system that chooses one possible successor of tasks. For example, we're looking at this task. Possible successors of this task could be, I mean, does anyone see how many? I mean, I can tell you there are 2 successors of this task. What can the 2 successors be? Sure.
I mean, we're executing this particular task multiple times, right?
Yes, the above sides times to be exact. Yeah.
Yeah, so we're executing it multiple times in a row. So then the task after this one will be this task as well, no?
Yes, that's one possible successor task.
Oh, okay, or the end of the program, maybe?
Yes, true.
Something like that?
That's 2 possible successors of this task. And once it has determined the successors, it then chooses one of the successors and continues the walk. And let's take a look at the assembly view. It's like on the right side, we see it looks like regular assembly because mostly is regular assembly. This is MIPS, DEG, NDN, but yeah. What's relevant in this walkthrough of the tasks is, so at the top we have the TARG spec. We see, I mean, it's a bit too small, but we have 2 labels saying outer and outer fallout. Outer is the one that's here. I mean, the clicker or something. Yeah, I'll just, here you see that we have no, you don't see the pointer, but whatever. On the topmost, we have the tag called outer. And in the bottom, we have the tag outer fallout. And between these, we find the task. That's the point of this TARG tags. And another thing that's important is notice that there's a small S flag on that instruction. That means that is the stop flag, which means you see it's a conditional expression. And if we take the condition of this expression, that means task is finished. Yes. And that's the first requirement of multiscalar programs. Let's have the second one. The second requirement is communication between tasks should be implemented as minimal ISA changes, which means we should mostly have a regular ISA and then add a few instructions that we need on top of that. No, I don't. I mean, I can. Yeah, okay. This is just, yeah, sure. It's quite, yeah, thank you. What we need to do here is we need to forward what we call the live out values. This is another compiler concept. Live out basically means a value inside a basic block that outlives the basic block itself. So imagine we have a value produced inside the basic block, and the basic block ends because of a jump, and then the value is still there. That's then what we call the live out value. What we need to do here is define the same concept for tasks, and then we need to forward the live out values to successor tasks, which is quite straightforward because that's also what's implicitly done if we're doing a control flow graph. The way we do that is we first try, I mean, imagine we're the compiler, we try to see what are the values that live out of this task. So here we have this is the, no, I don't even see where this, like in the red box, we have increment I by 1. So the incremented counter is 1 value produced by this task. And then we have the symbol read from the symbol list. We have the list header. We have the updated list pointer and the list element accessed by the LE function. Yes, list element, yeah. And how does this look like on the assembly level? It's like, let's go back to the assembly level again. Take a look on the top. We have another specification that's called the create mask. Inside, just note here that this program did not have the register names mapped yet, so it's all numbers, but it's okay. We also have 5 registers in the same number as values that live out the block. So the 5 values are on the right side. We have the mapping. We have the mapping of how the values map to the registers. But yeah, let's ignore that. And another important thing is here we have a lot of small f signs. That is what we call the forward bit. That we use these bits to denote now we produce the meaningful value, and then we forward this to the next task. There are also cases where we don't really forward those values. For example, temporaries inside the loop, we don't need them. So we release them using the release instruction. that means we don't really forward this, even though 8 and 17 are inside the create mask. There's also another release 4. Yeah. Okay, that's a very fast walkthrough of multiscalar programs. And the next section we have is multiscalar hardware. So now let's welcome back to the same diagram. Now we talk about the key components inside what's in a multiscalar hardware. So 3 key components: the sequencer, the processing element, and the address resolution buffer. I mean, apart from these 3 key components, people that are familiar with SOC designs, you will see on the right side is quite a traditional SOC. You don't really need, you don't really have anything more like that's more exotic inside here. So the first thing is the sequencer. That's the red box at the top. And the sequencer determines order of tasks, as we just like gave you a brief view about. It fetches the task descriptor. That's basically what will be generated from the 2 lines of comments apart, and also a lot of bits inside the assembly view we just had. That's the task descriptor. It fetches that task descriptor and executes the task. It basically sends it for execution to the processing elements. It also predicts the next task because we said they're successors, and it it picks by some kind of heuristics the next task and schedule that one as well. And the second important thing is the processing element itself. Apart from people may have heard about, for example, VLIW, very long instruction word, whatever. Those have dependent program counters on each other. But this one, all of these processing elements are independent on each other. They just fetch and execute instructions inside the task. And but you see, there's also the red ring that we talked about a bit earlier. That's a unidirectional ring that passes values, basically register values, that's passed between the tasks. We did forward and release and everything that's implemented by this ring. The third important component is the multiscalar hardware, address resolution buffer. Yes, the address resolution buffer holds speculative memory operations before they're retired. So basically the core, the process element issues a lot of memory operations, and they get captured by this address resolution buffer before all the tasks that before the task that contains all the speculative memory actions are deemed as, okay, you're retired. Now we can finalize these operations. And it basically detects and corrects dependency violations. If it fails to do that, it will then tell the sequencer, okay, scrap it. We don't like, this is the wrong task. Okay, that concludes multiscalar hardware and the multiscalar paradigm as well. I will now go into design analysis. So basically, we need a breakdown of useless CPU cycles, what would we say, when the CPU is not doing useful computation. So the objective is all Ps should do useful computation at all times. What we try to avoid is, the first one is squashing. We talked about this quite a lot just now because of wrong speculation. So either data or control. And we try to avoid stalling due to waiting for values. So if we need a value that's not come yet, that's what we try to avoid. And also idle due to no schedulable task. So if the sequencer does not know what to schedule now, of course, the Ps are going to sit idle. That's what we want to avoid as well. The solutions. So we have one observation is the incorrect prediction of branches causes squashing. That's one thing. The ways we solve that is actually quite complicated. We have 2 ways. The first easy way is actually the second one, is we optimize the code structure to reorder the branches so that we know that some branches are easier to predict, some are difficult. We try to make it always the easier to predict scenarios. Early validation means after predicting, we try to validate before the task runs too far. And if we came to know that it was the wrong prediction, we just terminate that task and free it up instead of letting it run to the point that we're really sure we did the wrong prediction. So the second observation is we have inter-task dependencies that serialize execution. Yes, this is also handleable by source level changes to reduce such dependencies. One example of such an inter-task dependency would be, imagine we run through a list with the accumulator to try to calculate the sum of all the values. What can happen is, because each task is the tasks are all trying to update the same accumulator value. That is quite inefficient because they have this conflict. Anyone who has taken parallel computing may know what I'm talking about, but the way to do this is we can we can split the accumulator value so that each task has a separate one, and then there's no problem anymore. Yeah. Third observation is short tasks may wait for very long tasks. This is basically if we have imbalanced tasks, some are very big, they will occupy all the PEs, and the smaller tasks don't really get a chance to execute in parallel. The way we solve this is also like we just perform load balancing by adjusting the granularity of the task. So make tasks relatively of similar sizes so that we don't really have two imbalanced tasks. Yeah, and we also do a comparison with other instruction level parallelism paradigms. So basically to show why the multiscalar paradigm is superior. So first of all, we do not require branch prediction on every branch. Remember that we predict control flows only when we don't know the next task. It's like that's, so we only do that on task edges. This will result in very large instruction windows, basically as large as tasks, instead of like regular triple O machines where we have branch prediction look ahead windows. That's basically the amount of instruction we can have in the window. The second advantage is we don't have to check load store conflicts on issuance, because checking load store conflicts on issuance results in a super complicated decode circuit. It's like we try to look ahead, look behind, and see if there are conflicts. If they are, we stall this instruction. That is handled here by the address resolution buffer in this design. So we just issue load store instructions and then resolve them afterwards. And we also have less complex hardware, because anyone who's taken a look at OO machine should know a lot of the, like, it looks nice on diagrams. It's actually really complicated on hardware because the retire stations and everything, you have a lot of very high fan out structure. In this design, instead of that, we can actually use very simple in-order cores as the added processing element to achieve relatively high instruction level parallelism. So yes, that's the design analysis. This is the last section, second last section of my presentation. That is evaluation of the example design. So we have a big NDN MIP simulator with cycle models. We have a 5-stage pipeline. We configure in and out of order or single or dual issue of the whole thing, of the simulated processor. We use a modified GCC compiler to generate the multiscalar programs, and we use benchmarks from the SpecFP suite at the time, and also GNU core utils. The evaluation that comes first is the increase in dynamic instruction count. Notice that we have an average of like about 10% in this sense. That is the first observation as well. We have more instructions in multiscalar. That means that is due to additional multiscalar data instructions, for example, release. That's the only one I've introduced, but there are a few other ones. Yeah. The second evaluation that comes is the comparison of a speed up comparison to scalar processors, and also the prediction accuracy in each setup, each benchmark. Yeah, we see that here we have lots of benchmarks which have different performance results, but we always look at the worst. It's just X list here. It has a very low speed up, actually less than 1. The line here is speed up equals to 1. Remember, we're comparing with scalar processors. This means this is even with 4 or 8 processing elements, we're still slower than the scalar scenario. Yeah, that is. But also note that up there, the red line shows that it has a relatively, actually the lowest prediction accuracy. And the best one is the CMP benchmark. It has a relatively high one, high speed up. It's actually almost 80% of theoretical speed up. That is, we have 4 elements, then 4 PEs, we should have at most 4 times speed up. Yeah. The observation from this is the speed up is largely correlated to task prediction accuracy. And also in suitable workloads, we have pretty good speed up. For example, the CMP, Tomcat V, WC, and example, those 4 are all GNU Core UTO benchmarks, which mean they're actually real world programs instead of just synthetic benchmarks. Yeah, you have a pretty good speed up in suitable workloads. And the final section is strengths and weaknesses of this paper. The strength is like the first one is this is a completely new paradigm at the time of presentation in 1995 compared to other IRP paradigms. So we have speculative control that has been proposed before this paper, but most importantly, we have speculative data. That means we don't resolve all dependencies at the first try. We try to defer that and resolve that afterwards. But also cooperation between software and hardware is also a very important key contribution in this paper. It's also work with very influential with large impact. We have, I mean, the citation is a very inaccurate way of measuring impact, but we do have a lot of citations, like over 1,300 citations in the 20 years of publication. That means, I don't know, we can calculate like 70 or so citations per year. The address resolution buffer is actually used by virtually all processors that's built today. It's better known as ROB or the reorder buffer. Yeah. And the whole paradigm is also known as speculative thread parallelism, or we also call thread level speculation. This is actually implemented in later products as well. So the IBM C++ compiler, and there's an extension to OpenMP, which is the parallel programming framework. That's called the TLS. So far with the strength, we have the weaknesses. So the first one then is also the one that I was not very happy about. It's like the important details on how to implement the most important components are glossed over. So how do we implement the sequencer? How do we implement the address resolution buffer? It's not covered, almost not covered at all inside the paper. In fact, this is actually one of the shortcomings as well, because time has proved the hardware is really difficult to design. There has never been a full real hardware of this multiscalar paradigm ever. The other issue is a weakness is that this design is severely dependent on compiler optimizations. I think, how many of you know the story of IEDM? Okay, so IEDM is basically a very ambitious design that shifted a lot of the responsibility of detecting dependencies to the compiler. And then that didn't work very well because especially this was actually a really old work in 1995. So back then we didn't even have as good compilers as nowadays. So we can say we have bad compilers that would lead to poor performance almost directly. And also the last one, which is just not that bad. This paper has relatively less vigorous evaluation, at least in today's standards. I know that this is what usually people call an opinion paper or something, but still, we don't even have a comparison with other ILP paradigms. We only have a baseline of the scalar. It's like, for example, how would OO do in this set of benchmarks? I have no idea. Yeah. And we also don't have like cycle-accurate simulation model or synthesizable implementations. I mean, those are quite common in nowadays architecture papers. Yes, that basically concludes my presentation on this paper. I would like to present the acknowledgements first before going to the discussion. So special thanks to the mentors of this presentation. They provided a lot of help and a lot of suggestions in how I should improve the presentation. And also thanks to the teaching team for picking the papers and teaching the basics of how to do an academic presentation. And the audience, which is you, for listening, and please engage in the discussion. Yes, and I will just go on to the discussion. Yes, so the first discussion point is how would this paradigm transfer into other fields? So we had a look at what we call thread level speculation, right? This means we speculatively execute a section of computer code inside a separate independent thread. If we also count hardware threads or processing elements as threads, that is what multiscalar paradigm did. And the question is then, how does a software implementation of such a TLS paradigm compare to the hardware-based approach? I mean, I have a few tips down there for you to consider, like task creation, how do you pass values between threads, and how do you roll back a bad execution of a thread. Any ideas?
What is that SMT here?
SMT, I'm sorry, SMT is symmetric multi-thread, symmetric multi-threading. That is basically all multi-core processors we have now. It's in comparison to AMT, which is all the processors aren't really symmetric to each other. Or you can just cover that and say all multi-core processors. It can be, it can also not be. It's like SMT basic concerns we have, for example, 4 cores inside the system. That is called SMT. SMP, I think, and that's the symmetric multi-processor. That's the issue. I think. Yes. I think I meant SMP. I'm sorry. I'm so sorry. Yes, it's a typo. Yes. Yeah, SMT4, SMT8, S6 in IBM processors. Yes. I mean, I can cover one of these aspects, these 3 aspects, to get people started. So, for example, in terms of task creation, we would require a dedicated thread as the sequencer in the software implementation, one that inspects all tasks and then like just creates threads and throws tasks at them. Or if you have a thread pool, you dispatch tasks to them. Whereas in hardware-based implementations, we have the sequencer hardware. It's like we don't really need another core, or we don't even need to, like, it can be very specialized. It just does the work of dispatching tasks. Yeah.
Yeah, just to clarify, task creation, isn't task creation done in the compiler?
Task creation, yes,
You
but
analyze the code and then you make
in multiscalar processors, yes. There can also be other designs where tasks are created on the fly, for example. Or it's like in OpenMP, there's one way that you just say OpenMP should just chop tasks into whatever like size it likes.
Okay, but how does OpenMP do it then? It's like on the fly, or?
OpenMP does it like you can the most, how do you say, the most common way that it does it is you mark this task interface on the for loop. I mean, you can give a block.
Oh.
And then inside it just creates, for example, iterations of for loop, branches of if as tasks.
Oh, okay.
Yeah.
So maybe passing values is just like passing messages in. Yeah, I've seen that in parallel programming, right?
Yes.
You pass messages between processes. Is that?
You can do that via, for example, shared memory. That is one way of doing that. Yes. And how do we do that in multiscalar processors?
I mean, how
we had a very like smirky face thing. We have this ring, right?
For this passing value, we had like special hardware support for passing. I mean,
yes,
2 things. There was the compiler flags plus hardware support, right?
Yes.
And then that would pass values
true.
automatically.
I think the most important thing actually is because OpenMP you also need compiler support for cutting the task. It's just by saying automatic, I mean the compiler handles that. I don't mean the runtime just cuts.
Oh, okay.
Yeah. But the difference is the the multiscalar processor has this dedicated hardware ring that just passes the values.
Yeah.
But with the software, you have to put it onto the, put it onto the memory.
Oh, okay, I see the point.
Yeah, I mean, even if you do shared memory or if you do message passing, it's software, so it all has to go through the memory system.
That's true.
Yeah.
But then the rollback, you do. I mean, what do you mean by rollback here in this slide?
For example, in multiscalar, when we did a miss speculation, and we then need to discard the results, stash the results. This same thing also exists on software implemented thread level speculation as well. Can you imagine how that would be implemented in software? Sure. Yes, we can throw away the frame. That's true. The other thing is you may also want to, for example, if everything goes to the memory, sure, you throw away the frame. But in high performance implementations, most likely you want to keep some registers, right? Now the registers, nobody's going to help you stash the registers in hardware. You would have to keep a window of the registers and restore them by yourself. Yes. But on hardware, for example, we could have implemented something like a shadow register banking. It's like we mark that this is the old copy, and then we switch on another copy of the register file, and if it didn't work out, we just throw the entire register file away.
Maybe it would help to clarify what exactly qualifies it. When does a rollback occur exactly?
Okay, so we do speculative loads, right? Inside that's what we define as thread level speculation. And at some point we discovered that we predicted that this address is going to hold this memory value. But then we discovered that the other thread actually wrote a different value in. And now we need to discard all our work because it may be that we depended our work on this value, which is now incorrect. Okay. We then need to discard the whole task. Yes, I think that's quite sufficient for this topic. If people want to learn more about thread level speculation, there's a paper, a nice survey actually. It helped me a lot in preparing these slides. A survey on thread level speculation technologies. I mean, techniques, yes. The second one is about IOP instruction models. So the multiscalar execution model, if we do a recall on that, we have control flow graph slicing. We have independent runtime task scheduling. That's the two characteristic designs that characterize multiscalar execution model. I would like, has anyone heard of what we call the explicit data graph execution? So this is basically a project developed by Microsoft and DARPA, and also afterwards by UTA, I think University of Texas Austin. And what happens here is like we have what we call data flow execution. We execute hyperblocks, which is kind of similar to what we call tasks on all Ps at the same time. We have one block, we throw it onto all Ps. We let the Ps just execute them in a data flow manner. Recall we had data flow circuits. Here we have this again, and then this is the data flow graph of this hyper block, and we schedule them onto all Ps and they flow. Yeah. Just want to see any kind of difference between these two, like the EDG and multiscalar. Sure, thank you.
I remember that at the very beginning, you said something about how the vector product, right, that would cause problems. You see, as we'd seen in the presentation, it's like a way to represent program that doesn't
really work as general processors.
I mean, it doesn't. When it has a PC, it doesn't have a PC, for example.
It doesn't have a program counter. Yes.
Yeah. Okay.
I mean, a pure data flow machine really doesn't have a program counter. But what's in the edge data, explicit data graph execution model is we have program counters that basically you can think of like this hyperblock is one huge instruction. And then we schedule that on. After that has finished, we schedule the next one on. But inside this huge instruction, there's no program counters as well. Yeah, I mean, I can say that maybe the difference is, yeah, I'll conclude this really quickly. It's like the difference is we schedule them all onto so first of all, we don't have a program counter inside each, like we don't have independent program counters in the programming, in the processing elements. We have one that denotes which hyperblock we're at. But Multiscalar basically has a lot of different program counters, each one for each processing element.
Oh.
And but similarities is EDG, I mean, Edge has also not had any hardware implementations, actually. I mean, it had some toy ones, but it also didn't pick up any serious movement. The reason is, I can guess the reason. It's a quite simple one that I mentioned in the weaknesses.
Oh.
Yeah, sure.
It's too complicated. I mean, you have to analyze a lot of dependencies and have a lot of access to instructions, and it just seems like a lot of
True. The
complication that
interconnection will get really complicated. That's one issue. Yes. Another issue is the compiler is really hard to build. Like that's almost all the case for why some of these really nice ideas died. For example, this one, but also Itanium is like it's really, really hard to build a compiler for those. So that really didn't happen. Then we just had crappy compilers, which made the performance suffer. So that was one thing. But maybe after several years, maybe 1 decade or something, which is now, it may be a good idea to take a look at these again. Yeah, that concludes my discussion session. And basically, thank you guys very much for attention. And thank you.
Did you send your presentation? I sent it to you. Could you send it on this ID as well? On
Okay, now it's working, right? Yes. So maybe I can I get the other one? Yes, sir. It's fine. Hello. So, yeah, so it's my pleasure to welcome Ignacio. Ignacio is a final year master student in Imperial College London, and he's doing his exchange program here for this semester. So Ignacio took this course to gain knowledge and insights on, how to read research papers, as well as, present and basically gain insights on how research works. And yeah, so he's going to present branch Runahead, which is something similar to what already you have seen in the first lecture. So yes, it's another speculative way to increase the performance. And Ignacio, all the best.
Yeah, thanks.
So, yes.
Thank you for that introduction. Yeah, so as my mentor said, I'm going to be presenting branch Runahead, an alternative to branch prediction for impossible to predict branches. Yes, it works. Okay. So to start off with kind of an overview of the executive summary, the motivation behind this paper is that increasingly programs are more data-driven. And this is causing problems for branch prediction. Branch prediction typically is history-based. It requires repetition. If you're just reading data and making predictions off that data, making decisions off that data, you don't necessarily have a pattern. So the goal is to provide an alternative for these hard to predict branches. And the main idea the author has is to process the instructions leading up to a branch in a coprocessor ahead of the main execution. And there's a few issues with this. The first is detecting the dependency chains at runtime. And the second is keeping these coroutines in sync with the processor, because you want them to run as far ahead as possible and without having to wait for the processor to catch up. And then we'll get to the results, which is overall, there's a branch misprediction per kilo instruction reduction of about 40%, and an instruction per cycle increase of 8%, which is lovely. So we're going to start off with some background. Pipelining. So I'm sure most of you guys know how pipelining works. I'll just give a quick introduction to it. Let's say you have these instructions. The most obvious way to execute them in a processor would just be to execute them in order, one after the other. So you do one, you finish, you do another, you finish, and you go. However, most of the time, the instructions don't necessarily use all the hardware at once. For example, in this imaginary setup, you have some fetching hardware, some decoding hardware, and some execution hardware. It's kind of a waste to let that part of the hardware sit idle while you could be using it for something else. So the idea is to pipeline it, to use different parts of the hardware at the same time, right? So first you fetch the first instruction, you have to start somewhere. And then while you're decoding the second instruction, you're already fetching, while you're decoding the first instruction, you're already fetching the second, and so on. You execute the first, decode the second, fetch the third. And if you keep going, by the time that you've finished with pipelining, you would have normally only been decoding the second instruction. So that's great. We're getting more instructions. We're getting a bigger, higher throughput of instructions. But the issue comes here, which is you've finished executing the first, decoded the second, finished fetching the third. What do you fetch now? So this branch here, this is a branch equals instruction. It compares x1 and x2, and if it's the same, jumps to L1. If not, it continues, right? So do you execute this instruction, the add-I, or do you jump and execute the next instruction? Thing is, we don't really know at this point because the dependency on this load hasn't finished executing. So what do? One idea is just to wait. So you just wait for the load to finish and then for the branch to finish. And at this point, you know what to do and you're done. But that's, again, wasting resources. So instead, what we're going to do is just guess. You guess one direction, in this case, the non-taken direction, and you keep going. Once you finish the original instruction, you say, okay, was I correct? If you weren't, you put them, you basically flush them, you kill them halfway through, and you keep going. So worst case scenario, it's the same as the no-ops. Best case scenario, you've already finished decoding the first instruction and fetched the second instruction. So it's overall a gain. This is great. You can start making better predictions. So you have a branch predictor that sort of takes history-based patterns and improves the guessing, but it's not foolproof. So yeah, simple solution, add bubbles. Branch prediction helps by improving your guessing, but this relies on branches being history-based, so repetition in some way. That's not always true. So if we look back at this instruction, this is data-driven. So if you look at this branch, it depends on a load. If this load loads data that's quite repetitive, branch prediction will work fine, no problem. But a lot of the time in fields like genome analysis, image processing, big data, it doesn't necessarily have a very simple repetitive process. So you're going to be mispredicting most of the, well, at least hopefully just 50% of the time, right? It's just a blind guess. So what are some alternatives? How can we get around this? One idea is to do a highly parallelized architecture. The idea is you essentially have multiple threads executing independent code. You dispatch, for example, a load in the first thread, and then you dispatch something from the second, the third, the fourth, and so on. And by the time you're going back to dispatching from the first instruction, it'll just have been finished executing, right? You hide the load latencies, the processing latency, and everything by just filling the pipeline with other independent instructions. And they're guaranteed to be independent because they're independent threads. And that kind of works. There's a bit of overhead for that. And also it's not suited for all kinds of workloads. So it can sometimes, it just doesn't always work. And we'll talk more about this later. And the second idea, it's not really implemented because of some very obvious problems, is just execute all paths. Duplicate your hardware. Whenever you reach a branch, do everything, and then fall back on whichever processor executed correctly. And this should work in theory, but again, you're wasting resources, right? You're duplicating your hardware for 2 branches and then just waiting for another branch for the other one. You'd rather be doing something useful with both sides all the time. And then this gets exponentially worse with pipeline depth. So if you have a pipeline depth of 17, for example, you might encounter multiple branches that you have to execute at all times. At some point, you either cut it off or you have 2 to the 17 cores, which not very good. The author proposes something else. Instead of splitting off at the point of reaching a branch, split off beforehand, have a smaller, not as powerful core, but something that just executes the instructions leading up to a branch, and resolve dependency chains for that branch in that small processor before the main core gets there. And we're going to talk about this. That's the main idea of the paper. So let's go into the mechanisms. Yeah, this key idea, there's 2 ways of implementing this. You can do it in software or hardware. In software, the idea is the compiler or the programmer will figure out what instructions need to happen to resolve a branch, and they'll spawn a thread. That thread will execute in parallel, and hopefully by the time the main processor gets to that branch, it will have finished execution, joined back up with the original main process, and have the results ready. This has a bit of high overhead because spawning threads isn't cheap. You also have to hope that that thread finishes executing. You can't really do this reliably for small branches, which limits how much you can apply this. And if there's only small dependency chains, like if it's just a load, it's a bit problematic. So the author proposes instead, let's do it in hardware. Have some kind of hardware that at runtime detects all the instructions leading up to a branch, basically what affects that branch, and execute them in a chain. So the idea is you'll have a loop. Inside a loop, you'll have some kind of branch. You detect all the instructions that come after that branch and all the way back into the branch. So you have a loop that can execute independently, making further and further predictions as you go on. And the nice thing about this is you don't need to change your source code, which makes programmers happy. So the first part is, how do you detect these branches? How do you know a branch is hard to predict? First introduction is a hard branch table. It's very similar to a branch prediction table. You have a bunch of addresses, and you keep count of how many times you mispredict. Every time you hit a branch and you mispredict, you increase the counter, say to 31. And depending on the implementation, that counter will have a certain number of bits. In this case, the authors proposed 5 bits, so 31 is a saturating point. All the bits are 1. Once it gets to that point, you consider that branch hard to predict. And the other mechanism is that every now and then you have to decrease these counters because every branch eventually mispredicts, and otherwise you'll just have everything as hard to predict. And also, if your code moves on to a different part of execution, that branch, that address, that hash of the address might point to a different branch that isn't actually hard to predict. So you want to decrease it periodically. So the author proposes 15 every 5,000 cycles. And once it reaches 0, you no longer consider it hard to predict. So now that you have these hard to predict branches, how do you detect them? And the idea is doing this backwards data flow walk over a buffer of all the previously retired micro-ops. So and then you store this sort of generated dependency chain in a cache with all the registers required to start the chain. So just to give a brief example, we'll give a better one later. Here, imagine this is your all the instructions that have been retired. You start off with your branch that just mispredicted and was hard to predict. You see what what does it depend on? So in x86, branches are dependent on some implicit CC register. So you say, okay, let's go up to the next instruction. Did this instruction modify the CC variable, and compares implicitly modify CC. So now your live instructions, live registers are P0, and you keep doing this. Here now your this instruction affects P0 by loading in from P2, and you continue so on and so forth all the way until you get back to your original instruction. And that's this loop behavior that I was talking about, right? You want this whole chain to be a loop. That way, once it finishes executing, you can immediately go back into the loop. And that lets you, on each iteration, since you're executing less instructions in the main processor, you can run further and further ahead, making predictions for further and further in the future than the core. So when do you trigger execution? There's 3 main things that you need to do. First is you have to make sure that the program counter of that chain is reached. So once you've detected this chain, the next time you reach the program counter of the first instruction, that's the first requirement to execute. And the second is, and the second is that all the live-in registers necessary are available, right? So in an out-of-order processor, sure, you might have reached the program counter, but that instruction won't necessarily finish executing for another couple cycles. You wait until all of the registers are ready. At that point, you copy those registers in your instructions into a coprocessor that runs on its own independently and continuously execute this chain. As you execute the chain, anytime you resolve a certain branch direction, you store it in a queue ready for the processor to reach that once, so that the processor can read the direction when it gets there. And when the processor reaches a certain branch, it checks, is there something in the queue? If there is, it'll use that to do its direction. And this queue will have a certain limit, right? There's, I think, for each chain, you'll have 5 items in the queue. And if you fully saturate that, you'll wait a little bit for the processor to catch up. And then you keep track of the accuracy, so you can modulate between this method and the typical branch predictor, as well as anytime you mispredict, you're going to want to resynchronize your chain, because it is only executing a subsection of a subset of the instructions, and it could be that something has changed and your chain is no longer actually valid. In that case, you want to resync it, get a new chain, get the new registers, and keep going. So some key insights and innovations. This has all mostly been done. Some of the ways that this author proposes are novel, but there have been previous papers to explore this idea of having a dependency chain execute on its own to predict branches. What this author proposes is to basically generate smaller chains that are dependent on each other. So you generate these interchain dependencies based on these small frequently changing branches within typical chains. So the issue that the author found was that so this is a bunch of test case, this is a suite of benchmarks. What he found was that in the in the dependency chains, there's a lot of small frequently changing branches, and anytime that branch changes, your dependency chain will no longer be valid because the code executed has changed, and you'll have to resynchronize with the CPU. Once you resynchronize, that's kind of, you've lost your advantage of being so far ahead to make better predictions. And it also has a bit of overhead to synchronize. So the idea is extract these frequently changing branches, somehow make them chains as well, and generate some kind of chain dependencies between these so that you can automatically figure out if certain frequently changing branches execute. And I'm going to give an example because it's a bit of, it is a bit complicated. So given a program like this, let's say you start at this instruction. It gets retired into your circular buffer and you keep moving. So you keep going on and on until you reach all the way back up and you reach the same instruction again. Now this instruction mispredicted. This triggers a backwards data flow walk. So we create a chain and we start at the bottom. We say, okay, this is our branch. We need to figure out what leads up to this branch. So this branch is dependent on X1 and X2. We look up the next instruction. The next instruction affects X2 and is dependent on X5. So we keep going. The next instruction affects X1. So on, this instruction has no effect on our branch, so we ignore it. All of these instructions have no effect, we ignore them. And we keep going until we reach the original one. And then we stop and we have our dependency chain. This can run independently on its own, but the issue is these instructions. Now, depending on if the top branch was taken or not taken, these instructions might execute and they might not. In this example, they executed, right? The branch wasn't taken, so you ended up executing. Otherwise, they'd be skipped by jumping all the way to this add instruction, which is labeled L1 here. And essentially, the outcome of this chain will change the chain itself. This is a problem because if you want this to if this is frequently changing, this chain is going to get out of sync quite fast, right? These instructions might affect the outcome as well. So the author proposes, instead of doing that, you start off the same, you start walking up the tree, up the chain of instructions, and you stop here. You have special hardware that resolves the merge point of the instruction. So that branch equals instruction has two branches. One branch jumps to L1 and the other one just keeps going. These are the two arms of the branch, essentially. They resolve at L1 because no matter which way you go, eventually you're going to hit L1. There's some custom hardware that he's added to make this possible. But you essentially stop here with your first chain. And then you continue. You look for the next branch here. And this branch, if it's a hard to predict branch, you add it to the next chain, but you keep moving your way up from this one. So now you do the backwards data flow walk over this, moving all the way up to the original instruction, and you stop. Now, why this is good is given this, you know that this second chain will only ever trigger if the first branch is not taken. So you label this branch as A not taken, and you only ever execute it should you finish chain A, you come to a not taken branch. Instead of immediately looping back, you'll start executing the chain B, and then you'll keep going, right? So it allows the processor to be independent for longer. It doesn't need to synchronize, which means it can go further ahead and make predictions further in the future without needing to synchronize and basically losing all the progress it's made. So move on to these key insights and innovations, detecting these frequently changing branches using this merge point. And then using these to generate interchain dependencies that allow the processor to run ahead further, just be independent for longer. Independent for longer. So let's talk about some of the results from this paper. paper first, it was all the testing was done on a simulation. There's no real hardware. It was simulated on a cycle accurate x86 extension simulator with some custom extensions for this branch run ahead. And the basic configurations like this, if anyone's interested. The results, so the test was done on 4 hardware configurations. The first is this Tage SCL. That's a history-based branch predictor. So that's one test. And then there's 3 configurations for the branch run ahead: the core only, the mini BR, and the big BR. And the difference between them is how many resources they use. So the core only, it's the least resources necessary, but it does share some of those. It does require sharing some resources with the main core. So for example, the register file, the PRF here, it has no dedicated register file. It has to share the register file with the main core. So for out of order processing, you have a register file and it shares it with the main core. The mini gets a little bit more. It gets its own register file. It gets its own hardware. And then the big or the unlimited, the idea is just give it as many resources as possible, make it big enough so that you should never really ever saturate all the resources. Just if you could just run this without ever having any reason to stall because of limited resources, that's the big unlimited. It's not something that would realistically ever be made, but it's just to sort of have a benchmark of how good could this idea work in practice. So we'll look at some of the results. So this is just for the instructions per cycle with the 4 tests, and this is all compared. This improvement is all compared to the base configuration from before. So as you can see, overall, it just seems like this seems to work. Most of the graphs are positive. I'm going to bring attention to this one here, where we see actually quite a significant decrease in instructions per cycle, down to about -8%. And this goes back to that whole sharing the resources. The branch run ahead, since it's sharing resources with the main core, it's actually slowing down in this scenario the actual execution of the main core, which is sometimes fine. In fact, for most cases, it's fine because the benefit of the correct branch predictions outweighs that slight slowdown that happens due to fighting for these resources. It doesn't happen in this case, so you do see that that dip in performance. However, as soon as you give the predictor some of its own resources, it stops fighting with the main core for access to these resources, and you see the over 10% improvement. And on average, we see 8% increase in instructions per cycle, which is good. And if we move on now to the mispredictions, which is kind of what it's trying to address, we see on average around 40% increase, 40% improvement, which is a 40% decrease in the mispredictions per kill instruction. And back to this example here, right? You can see that it didn't help the mispredictions quite as much when it was sharing resources, and that's because again it was sharing resources. So both the core was slowing down, which decreased the instructions per cycle, and the branch run ahead wasn't able to do that run ahead. It wasn't able to get ahead of the main core as effectively because it was sharing resources. So the author suggests these IPC increase and the branch misprediction decrease is that I've quoted here is for the mini BR, which is what the author proposes as the best, like the most useful solution. Oh, sorry. And one more thing I wanted to comment on is that if you look at most of these graphs, there's the mini BR, sorry, the mini BR and the big BR are quite close, which suggests that the amount of resources given by the author is, for all intents and purposes, almost as good as the perfect branch run ahead using this method. So yeah, I'm going to put up the executive summary here. If anyone has any questions, we can do a quick round of questions now, if anyone has any. no, we can move on to the analysis where I'll give the strengths and weaknesses. So let's do that. Yeah, so the analysis. There's a couple of key strengths that I want to talk about. First is that it doesn't, this idea doesn't require modifying the ISA, which is useful because it means it could actually be implemented in a reasonable amount of time. Anything that requires modifying the ISA also requires a lot of software support. It's just a much bigger change, whereas this could be implemented in the next generation of processors. Well, in this current generation of processors, but the next actual processor as simply an addition, something that helps on alongside the branch predictor. Also, the results do suggest significant improvement. 8% increase in instruction per cycle is quite good, but especially the misprediction decrease of 50% is quite significant. And I think the paper just in general is quite well laid out. It's easy to follow. The design is described relatively well, especially since it isn't exactly the most straightforward concept. And it does lay out how it could potentially be implemented. It doesn't just say, oh, if we did this, we would get this performance. It has some kind of simulation, some kind of idea of how it could potentially be implemented in real hardware. I wanted to break novelty out into its own section because I wouldn't quite consider it a strength nor a weakness. There's other papers that have already used Runahead for other topics as well as this one. So one paper that's of interest is Runahead execution, an effective alternative to large instruction windows. This paper explored using the Runahead not to predict branches, but rather to predict, to run ahead and pre-fetch data. So instead of using a prefetcher, it would run ahead and do all the loads ahead of time for the processor. And then this other paper here, this difficult branch prediction using subordinate microthreads, is quite similar to this paper in the sense that it's using them to predict branches. It's using these, it calls it microthreads to predict branches. This paper introduced the idea, and over the years it's kind of been refined. This is what I would say this paper is doing. It had a lot of issues with finding dependencies, which this paper addresses a lot better than in that paper. And also, a lot of the time, the threads weren't able to finish before they were needed. And that was one of the main difficulties in that paper. Also, the threads didn't execute independently for very long. There's a lot of issues that existed then that have been improved by this paper and others that have come between them. And yeah, so I want to bring back to this point. The key insight here is the interdependency between the chains. So being able to trigger one chain from another without needing to resynchronize and figure out what the new chain would look like. So some of the weaknesses, it doesn't compare results against previous models. So it just says, oh, this is if we didn't have the branch prediction, and this is if we do have our branch run ahead. Which obviously does show improvement because it is able to do something that branch prediction just isn't able to, right? It just enables it in some circumstances. It would be interesting to see how it might compare to that previous paper with the microthreads or something else. You can't really compare them looking just at the papers themselves because they're all based on different base models. I mean, the other paper was nearly 20 years old. I mean, computer architecture has gone a long way. They're using different bases. So it would be interesting to see how this improves on previous run-ahead models. And then the author in a few parts of in the introduction of the paper cites some of these alternatives and criticizes them for being too dependent on the branch predictor. I don't really see why that's quite relevant. And also this system also depends a lot on the branch predictor to figure out if something's a hard to predict branch to trigger the generation of branches. It's kind of a supplementary feature to the branch predictor rather than its own completely independent system. So yeah, any questions on that before we go into some lead discussion? Any questions on any of what was discussed? Just see. If not, we'll move the discussion? Cool. Yeah, so discussion. So said we'd come back to the highly parallelized architectures. And I want to contrast this idea of highly parallelized architectures with this branch run ahead and what might be different between the two, why one might be better than the other, why just switching between threads isn't necessarily always useful for different for different workloads. So I don't know if anyone has any ideas or start pulling up some of my own.
Yes, so one thing I can see maybe is that you're switching between threads, you're still using the same core, right?
Yes.
Yeah, so then you have overhead to load the correct registers. Because
Yeah,
if you
so
switch
there-
between threads, then it's not the same like context basically. Switch context, right?
Yeah. So that is one issue with that's part of the overhead of highly parallelized architecture. You have to have something in place to deal with, okay, this thread or this process or whatever you're switching between. Is it going to share resources with the other threads? What resources is it going to share? Do you want it to be completely secluded? There is that's kind of the overhead that you pay with that. But you can solve a lot of these problems in hardware. It's not exactly zero cost, but then again, neither is this branch run ahead. So there is cost to be had. Oh yeah, that was that. So I think one interesting thing would be talking about throughput. So I don't know if anyone can sort of think of any reason throughput might be different between these two. Well, I think throughput is one of those things where highly parallelized architectures do quite well. So the idea is you can, say you have a program that typically just executing on a single thread, on a single thread might take 10 minutes to execute, right? But if you hide some of those latencies through this switching, you might be able to execute it overall in 8 minutes. That said, you do need 10 of these threads. So for example, if you have 10 of these threads going, you might be able to execute in 8 minutes. That means that overall your execution time is actually 80 minutes, but per each version of the code, you're finishing everything in. So if you do 80 minutes divided by the 10, you execute each one in 8 minutes. So you do improve the throughput because overall you're getting 8 outputs. So you're getting one output every 8 minutes on average, but you also don't get the first output until after 80 minutes. And that goes into latency. If you're switching constantly between one, like each one will take a total longer amount of time to finish, but in that span of time, you can finish a lot of these threads. Don't know if that quite makes sense. Yes.
Just a quick question to
Yeah.
try to understand. When you switch between threads, how do you do that exactly? Do you do that like ahead of time? Because as far as I'm aware, to switch between process, it's pretty costly to go back to the OS and then see which process you need to schedule. There's a lot of overhead in switching processes. So is there a better way maybe that has less latency, better throughput, or?
Yeah, so it wouldn't, there would have to be a lot of hardware support. So yes, it depends massively on how you implement this parallelism. I should have specified when I mean a highly parallelized architecture, I mean you have significant hardware support where you can just kind of execute one instruction from one thread, then move on to the next instruction from the second thread, go on to a third thread and just pick up an instruction. You end up filling the pipeline with instructions from different threads instead of having to go all the way to the OS. This is built into the hardware. It's more for massively dispatching processes rather than maybe user level stuff. But yeah, that's what I meant by that. But yeah, so the latency overall, you have to still wait a lot longer on highly parallelized architectures to get the first results. But then in a given period of time, you'll get a lot of results. So if you're willing to wait that time, it might be useful. If not, it might not. And then this branch Runahead, what it does help is in single threaded process. So like in a single core, in a single thread, you're able to pick up this you're able to improve the you don't have to, in a single thread, you can basically hide all this latency by just ahead of time figuring out what the branches are. And then complexity is an interesting one. This is kind of up in the air. It could be for either one. The design of this branch Runahead is not overly complex. It doesn't take up too many resources, and it kind of works well with everything else. Was like you were saying, it can get very complicated to deal with multiple threads, and once you trying to manage all the hardware and everything, it can be quite complex. So it's just some ideas. I don't know if anyone has any other thing they want to bring up with this. Give it a second. No? Cool. Security. So I think this is something quite interesting and very relevant nowadays. The paper doesn't mention security at all. I was going to put it in as one of the weaknesses, but it really isn't what the paper is trying to describe. So I don't think it quite belongs there, but it is very interesting to talk about. So yeah, I don't know if anyone can think of any security implications of this device or think of any sort of recent hardware bugs that might be similar, that might be able to be exploited in this way. If anyone has an idea, if not, I can give one. I don't know if it's all of them, but yeah.
I mean, I guess in the same way of like a lot of traditional side channel attacks, for example, it's like because you share more resources, you potentially also leak them to other threads. And I mean, that's not even side channel attacks. Maybe you can just leak things directly. I mean, but also even if you don't leak things directly, still like timing issues or cache issues. I mean, it's not specific to this design, but just sharing resources in general may lead to, how to say, security issues.
Yeah, absolutely. I think it's a very good point. Basically, like you said, there's a lot of, by adding any kind of hardware that shares resources, you're going to add side channels. That might be very complicated to figure out. So I don't know if any of you know about Spectre. I'm sure most of you have at least heard of it. Spectre v1 works by training the branch predictor to execute some malicious code, and then that malicious code leaves some kind of observable state change in the cache. So for example, you execute some code, you train the branch predictor to think, oh yeah, this is okay, and then you switch part of that code, so you pass in a different pointer that should be illegal to access, but the branch predictor says, oh, that's fine, do execute it. It starts executing it. It actually does load in that pointer that you shouldn't have access to. And by the time the main core by the time the core realizes, oh, I shouldn't have done that, it flushes the internal state of the CPU, but it doesn't necessarily remove that loaded value from cache. And I was thinking, if you have this, could you potentially inject malicious dependency chains? So these dependency chains might run one cycle ahead, they might run 2, 3, 5 iterations ahead of the main core. And if you could reliably get 5 iterations of of malicious code executed, that could significantly increase the ability to read or exploit this sort of this speculative execution. The side channels based on the speculative execution. And also just kind of built up on this, how do we handle exceptions? So with Spectre, you do load, but then eventually the processor realizes, oh, I shouldn't have done that. It throws an exception, and then there's a whole system of calls to the OS or whatever is in place to deal with that exception. But in this branch Runahead, it's similar to out of order processing. You don't actually necessarily execute this this code. So what do you do if you try loading something that should have been an exception? How do you deal with that? There's just no information. What happens if you do reach a valid exception that the main core was eventually going to run into? Could that also be another use for this branch Runahead to predict these exceptions and start doing some of the process for these OS calls, which are quite expensive? Yeah, or could you somehow detect that since you're so far ahead, you might be able to do extra memory checks before loading in data. Could you run ahead to these points in memory, do the bounds checks before they're even executed by the CPU and prevent something like Spectre v1? Just some ideas. Don't know if any of you have anything to add to any of these, any objections? Maybe I got something wrong. maybe you have something else that another idea of what, if you're running ahead, what else can you sort of predict? What can you get to and figure out before it's necessary? Yeah.
If you're running ahead, isn't it the case that maybe in some cases you can also load stuff from memory in advance?
You do load stuff in from memory. So loads are something that you could, in a dependency chain. Actually, one of the ones we saw, you actually have to deal
Because
with.
here the focus was really on the branch misprediction, right? But then you could also try to, because as we see in this class multiple times, a huge like cost is also waiting for data, right? Waiting around for data. So yeah, I don't know how much it would improve it.
I mean, that's been explored, actually. One of the papers I brought up earlier by Mutlu, he was using this sort of run ahead to go ahead and read this data beforehand. So you don't have to, wait and pay that cost of the latency of memory. It can be quite high. So if you could just run ahead and pick all that up accurately, then that would be very useful. And so that is something I'd explore. And actually in these, in the dependency chains here, you'll have loads sometimes that you need to do, and those will eventually be necessary by the CPU, hopefully, if your chain is correct. So in that sense, it can also help reduce the penalty of waiting for memory. Yeah. Oh yeah. So another point. The author disregarded software solutions because it's too slow. You have to you spawn a new thread. It sucks. And he proposed a hardware only solution, but he also proposed one that only disregards. He proposed something that only required sort of kind of adding something to the ISA. So I don't know if any of you guys can think of anything that might be useful to sort of split the cost. Is there anything you could do in software and in hardware? So maybe, I don't know if that sparks any ideas for anyone. Yeah.
In software, are you talking maybe about like static analysis, like analyzing the branch predictions ahead of actual like running?
Yeah, that'd be a very good way, I think.
I mean, yeah. But I fail to see what else, like non-statically, like dynamically, what you could do.
Well, yeah. So that's kind of where I was hoping to go with that. Is you have some sort of I'm just going to put them on here. You have some sort of static analysis at compile time, maybe, and you can take advantage of some extra context that's available at the source level. So programming languages will have some kind of construct, and you might be able to use that to learn more about the intent of the program and sort of figure out if a certain dependency chain if a certain branch might be hard to predict later on. And you can mark those, for example, this is just an idea, at the instruction level. So you could say, oh, these instructions lead up to a certain branch. And then you can simplify the process of extracting these dependency chains by just having it sort of built into the instructions themselves. So you can have them immediately. You don't have to wait for a lot of mispredictions. You can immediately know, oh, I should spawn in a dependent chain based on what the compilers told me. I don't know if anyone has any opinions as to why this might not be as good. Yes.
You have maybe you have what you talked about. There is like it's not obvious what is a chain, right?
Mhm.
Like, because you can have a branch in the middle of the chain, kind of, and then it splits the chain apart, if I understood correctly.
Yeah.
And so then it's unclear what you should mark as a chain and when you should begin actually, you know, when you're actually making the chain ahead of time and not going back in time to make the chain, then you're not sure, like, oh, should I start here or should I start after the branch? Maybe that's what you're referring to.
Yeah, I mean, that's essentially it is. It's just really hard. It happens, a similar comparison might be compiler scheduling. So compilers will nowadays have very complicated scheduling algorithms, but compared to out of order processors, they're just not quite as good. And that's because when you're at runtime, it's hard to necessarily predict what the code might be doing, but also certain parts of the code might benefit from being scheduled one way in some context and another way in a different context, and you can't quite do that statically. So you might miss opportunities for scheduling. Your chains might not always be correct, and like you said, depending on the execution, you might end up with sometimes the chain looking one way, sometimes the chain looking another way. It's not obvious how to do it, and then yeah, you're just kind of pushing the problem to someone else as well. You're pushing it to the compiler. So that's yeah. So it's not necessarily clear if it would be a good idea. Be interesting to explore to see what could come out of it. And I have, I think, just one more discussion point, which is why are we predicting at all? Why do we have to make predictions? Can we not just execute something we know should be fine? So the author implements a way of detecting branch merge points. Could we somehow use these to find instructions that are independent and at that merge point that we know no matter what way our branches go? Can we find instructions at that merge point which we can already go ahead and start executing? So I don't know if anyone can think of any way of doing that. If that would be a good idea, if it's not a good idea. Any opinions? Yeah, so one potential problem with that might be, can we ensure that there's no data dependency between that merge point instruction and the two branches? So if we can do that, that's great. But that might be complicated, especially depending on the size of the branches. And that kind of goes on to this problem, which is, do these independent instructions even exist? I mean, if you have a merge point, why would you put it after the merge point? Like if the instructions are dependent on the branch, why would you put it after? It might actually have already been scheduled ahead of time. I don't know if they exist. I couldn't find anything to indicate that they do exist, but it'd be interesting to analyze some of those benchmarks, see if, are there merge points that have independent instructions that we can analyze afterwards, and use some of the hardware described here, but for a completely different purpose. Of course, this wouldn't always work because it's unlikely that there will always be independent instructions. So it would, again, be a sort of a supplementary feature on top of the branch predictor to minimize how often you have to predict. So I don't know if that anyone has anything you want to add off that. Yeah. If not, I'd like to thank my mentors who helped me a lot with all of this stuff. And yeah, thanks for listening.
Okay, thanks. I'll make a couple of comments. Maybe Rahul can put me up also. I don't know if you can see.
I mean, I have 8 p.m. slot. My friend had the.
Can you hear me?
5.
I think we can hear you. Can you hear us, Onur?
Okay,
I'm just
now-
setting up the.
Yeah, now I can hear you.
Yeah.
Yeah, thanks for the presentations today. Today was the single threaded performance session, let's say, which is a very old topic, and we covered a very old paper almost 30 years ago, and a relatively new paper. I'll just make a couple of quick comments. I think the discussion on the second paper was really nice, actually. It covered a lot of topics, I think, that has been keeping people busy on improving single thread performance for a long time. And you can see that the pursuit still continues, but it's hard to achieve very large gains at low overhead. And that's going to be the important thing to look at going into the future. As mentioned, a lot of the basic ideas like Runahead execution, simultaneous subordinate microthreading that this paper builds on were developed in early 2000s, if not earlier. And this paper is kind of massaging them to be more powerful and hopefully more efficient at the same time by using these dependence chain detection and better identification of hard to predict branches. So in that sense, there's progress, but if you can also see that the ideas are relatively incremental because this is a topic that has been looked at for decades and decades and decades. It's very hard to come up with something that's completely disruptive, right? We didn't. This is to contrast this with last week's talks. We talked about processing in memory. Yes, the idea of processing in memory had been around, but no one had looked at, for example, doing a bulk bitwise computation in DRAM. So that has changed, for example. So that's the difference, I think, in terms of the type of topic. Compute-centric world has a lot of things that have been looked at, whereas the data-centric world is just coming up. People have not looked at things that much. So I will make a comment on multiscalar also. I don't know, your video stopped. Can you guys still hear me over there?
Yeah, can you hear us, Onur?
I can hear you, but I cannot see you moving. Yeah.
Yeah, things are not just
Okay.
give us one sec.
I mean, if you're hearing me, that's fine. I don't want to delay people more than needed, but I'll make a comment on multiscalar. Multiscalar had a lot of influence as was mentioned in the presentation, and it is a nice execution model, and it has the nice effect of parallelizing many different tasks from a single-threaded program. The difficulties usually is around like how to form the tasks. That's always a tough question, and also how to communicate between tasks. In the end, it becomes communication limited, and the hardware proposed for multiscalar was not, let's say, simple at the time, and it's even not as simple today also. But it has influenced a lot of work that came afterwards on thread level speculation, and also different sort of execution models like the TRIPS execution model, which later led to the edge architecture that was mentioned. So in that sense, it has had quite influence on academic research and somewhat on real systems as well. So it's good to think about execution models in that sense. But maybe it's time to think about execution models from a data-centric perspective. If you look at multiscalar and a lot of the execution models, they're all compute-centric execution models. There should be some data-centric execution models going forward, and that there's a lot of room for research in that direction because there are not that many works in that area. Okay, I don't have any other comments. I still don't see you guys moving, but maybe it's okay as long as you've heard me.
Yeah,
No problem.
we are hearing you loud and clear, but it's just the
Okay.
video stopped working, I guess. Yeah.
Okay, that's fine. Yeah, I don't have any other comments. If Rahul or someone else has comments, they can make them and maybe close the session.
Yeah, I think I have just one comment. So like as Professor Mutlu also mentioned, right? So these research area is still like much active as it used to be, let's say, 30, 40 years back. So yeah, I mean, I agree with what Professor Mutlu says, that I mean, it's always good to think about these works, and then if we can make some fundamental novel observations and novel ideas coming out of these directions, and they have like much more let's say impact on pushing the performance limits of today's processor, what superscalar processor means basically. So yeah, if you don't have any other questions, I think we can call it a day for today. Yeah. Okay. Hope to see you in the next class. Yeah. Bye-bye.